to actually get us to that point to be able to actually solve a level one problem. But let's discuss that level one problem, right? So, who drives? Anyone drive? Who's driven in DC traffic? Yes, right? So there's a lot of things that we face in traffic, right? But one of the anomalies that I've seen in this city that's very unique, that I think is very much a problem, is when you're driving in traffic and you're stuck behind a long line in a fire truck or an ambulance is stuck. I'm thinking about this if you were actually coming and having an emergency and you needed somebody to come help you, and they're stuck behind all the cars on Sherman Avenue. So, between this problem, right? I talked to some firefighters and they told me some things that they face when they're driving or trying to get to their routes, right? Traffic, bikers, scooters, and Amazon drivers, right? So when I asked firefighters what they want to kind of mitigate this problem, they gave me a few suggestions, right? A warning that gives to the driver that the fire truck is coming, right? Some device that works with the strobe light sensor on the top of the fire trucks that, signals to the traffic lights to turn and needs to get the right way, right? More of a visual aid, so now we're in technologies where you can actually have these visual aids right in your windshield, or something that gives you a visual aid, and a countdown that lets you know, like, hey, when a fire truck is actually approaching like 500, 400, 300 feet, right? Taking this feedback, I came up with the solution of quantum corners, right? Quantum corners is a threefold phase quantum sensor, right? That's quantum sensing that uses LiDAR capabilities with signal photon detection, and then quantum computing, which would be based off of a SLAM algorithm, so we do a 3D reconstruction system, and then quantum communications would do GPS rerouting. Now that was a lot, but we're not there yet, but I have commercial off-the-shelf products that I want to actually use to build a foundation so when we get to that quantum technology. So that's what I have right now, right? So everything that you see on to the left is my quantum sensor prototype that I'm working with, right? I have all the way to the right, that is a small FPGA on top of Arduino, the Intel Cycle 10. I have nipples, my main processor in the middle, and I also have a LiDAR that I will use along with an RGB depth camera for vision. And that will interface what you see on the right, which is actually the Opticon device that's on the top of the traffic lights where you flick on and you get the it's called the fire truck the right way when you're going. So interfacing with that in a short amount of time to be able to give that right away to where you get that signal back to the driver to say, hey, you have a fire truck coming, get out of the way. There's for the quantum sensor, like I said before. Now let's dive into the work that I've actually done to actually get us to that point. So let's just do understanding 3D reconstruction in general, right? 3D reconstruction is very much cool with computer vision, and we're trying to do like 3D maps like if you've driven in a Tesla before, where something comes up on your right and it pops up on the map right away. That's 3D reconstruction, right? So the general flow is take an image, get some depth information, pair those together to where now we get 3D points, put those together in a point cloud format. Now we have STL files that we can actually do to print it out, right? That looks kind of ugly, right? But let me give you a more accurate picture. So say I have this teddy bear, right? I take and get the point cloud information from that teddy bear, right? Now, I do some smoothing of it, and I can actually now get the print out of that teddy bear. You can kind of see it right there, right? This is very rough, but it's just the idea, right? Now, that's just one single image, right? Imagine an entire video frame, you have different images coming from different angles, right? You want to kind of merge those images together to get all the point clouds in one big point cloud. Doing that, you get about really like thousands and thousands of points, right? So to kind of like mitigate it, you got to kind of downsample them. But sometimes that put holes in the point cloud, so now we have some gaps, right? And these gaps show up in kind of a 3D reconstruction to where it's a little bit janky, right? Same thing when we see the plant. See the plant here, this is the 3D correction of the point cloud. Now we get some reconstruction, it's a little bit dark. Oh, my press connection. Wait, did you? Yeah, did you see?
Try to escape it.
Okay, there we go. So now this is the same thing where I have all my different images from different angles merged together, trying to reconstruct it. I got some gaps in it. Now we get this big blown up image, right? So trying to fix that is really what we're trying to get to have this foundation, right? So that dives into looking at the SLAM algorithm, right? Now, why would I look into the SLAM algorithm even for this problem, right? Because SLAM is simultaneously localization mapping. What does mapping have to do with this, right? In those images, right? Yes, we go through this whole entire loop of going ahead and getting a map image, right? So we get this image and then we get a map of everything. But in this map, we have different map points that we can actually use for our point cloud so that we can get our 3D reconstruction. And the thing is, even when we're going through the SLAM algorithm, we're capped at a certain amount of points. So if I'm doing it regular, just 3D reconstruction, what I just showed you before, I might get up to thousands of points. But SLAM, especially with this plant, I've seen it is capped out around about 735 points each time I run. Doesn't matter how many images I'm doing, it removes different images to where now I have 735 much smaller, to be able to still get this ugly picture, right? But it's less points. So now taking that, right, we want to do this in real time, right? So now that we want to do this in real time, we have to find out the bottleneck of the system. The bottleneck of the system actually happens to be the full bundle adjustment, right? The full bundle adjustment is this all the way to the left, where basically I get all these 3 key points, right? And now I have to edit them and make sure that they're pretty much accurate, but based off of the other points that I observed. So that brings us to a bundle adjustment example. So now imagine I have an image, a 3D image, and I'm just taking pictures of it all the way around, extracting different points, right? And I'm comparing those points against each other over and over and over again. It's like just doing something very slow, just taking the slope over and over and over. That problem is called the Markov problem, right? So now it's the mix between doing gradient descent, which is regular stuff that we know, and also Gaussian-Newton. So when I'm far away, I'm doing gradient descent. Sorry, you do gradient descent, which is slow. When I'm close, I'm doing when I'm far away, I'm doing Gaussian-Newton to try and get faster. When I'm close to it, I'm doing gradient descent to find the actual solution. And when I'm trying to find a solution, I just keep doing it over and over until I get like to close match, so almost converges. That, if you would think over and over, takes a lot of computations to solve a profile, right? So we said, let's do not any more direct computation. Let's just try and do it just straight with machine learning, specifically a graph network. If I take all these points and I map them together, it gives a graph-like structure. Now this is me kind of using like visual learning, like to be able to look at the structure of it and say, how can I just inference on it and see where it's at? So this is our graph neural network. We basically extract all the final map points in the observations. We put them as inputs to our entire graph neural network. We train on that graph. We put that as a graph as an input, and then we train on that graph over and over. So the metrics to see how well we are doing, right? We want to look at accuracy, which is the absolute trajectory error that comes from the map when you run through the SLAM algorithm. So how close you are to the ground truth, it does like pretty much a subtraction to see how close you are. And that's what we're going to use to measure to see how accurate our algorithms work. So that's what it looks like at the top, right? Pretty much you'll see like a little red in between the black and the blue. Black is ground truth. The blue is what you actually did when you ran the algorithm. And you just want to see as little as red as possible. And then they give you an actual root mean square number that we want to see it compared to. And then just mean tracking time is what we started off with, right? So we started off with mean tracking time because that was actually just how long it takes to do the whole process. So some of our challenges and results, right? So we got to see that the graphs look similar when we use the control versus the graph neural network, Markov and the graph neural network, which is our method, right? But if we look down to the bottom, we start to see a little bit of convergence, right? So we've seen that the graph neural network solution has variable performance depending on the characteristic data set. Let's focus on these last two right now, where we see poor convergence, right? That last one actually happens to be 3D reconstruction. So that's why I started my talk off, because once we went through and looked at the different data sets, we see that 3D reconstruction is really the worst. And that's really the one that we want to care about the most. So now, this is what our original graph neural network was doing. We did some retraining, and we kind of overfit. We did. But, still poor, but we got some better results, but we didn't think overfitting would be the best thing, but we did get some decrease in percent error by about 99%, even though it's still in the 2000s, which is pretty high. It's bad. But just to see that it wasn't just biased, I tested on a different data set with this image of the teddy bear, right? So this is the control and seeing how it looks. And we get something similar with that when it comes to the graph neural network. So we wanted to see what was the disadvantage, right? It's the output map accuracy. So we started looking at the error versus the different pose pairs. So amount of pose position orientation pairs that they do as you go through the algorithm. So the longer you go through the algorithm, you have more pairs, right? We want to see the accuracy as you have more pairs. And we start to see this kind of like trend towards this area right here where we see these amount of pairs and we see the graph neural network start to act up with accuracy. And so now when we look at the accuracy, we bring to the timestamp, so actually trying to figure out where in the algorithm where you start to see this failure at, you see it happens towards this time end. And now that we found this, right, in this video, we can actually isolate where the algorithm starts to act poorly. So now let's go back to the timestamp, right? Looking at the disadvantage, right? Now I can map in that time where we're actually seeing where it's poorly. And what we noticed is, so this is the control, it's looking fine, it's what it should look like. But this is the output that we see when we see graph neural network, pretty much that similar image that we had before, right? And this actually technically happens at when a loop is detected. So we're seeing that our graph neural network is actually failing when it detects a loop to actually do global bundle adjustment. So it's really struggling with that. But because we have a reason for doing this, what is the reason to do this? We want to have the speed up, right? We want to do this faster because even if we're having bad accuracy, at least we can see if we have the speed up. Or if we don't have the speed up, then there's no point in doing this. And we compared our mean time. There was no difference in mean time, right? So that was kind of disheartening at first, but we thought about it. We're actually only really doing the graph neural network on bundle adjustment. And the bundle adjustment happens, the global bundle adjustment happens when we see loop close. So we had to test it based at the very end when we see the loop close. So less timestamps, right? Kind of similar to what we just seen right here. So this is about like what, 5 seconds, 5-second range. So at the end of this algorithm, we can do the timestamp to see how it goes. So this is the control with the graph, this is the global bundle adjustment with the control. You see the highest spike is about almost 3,000 milliseconds to do the global bundle adjustment. That's pretty long and it takes a lot of time, right? Now, our highest peak over here, even though my graph is a little skewed with my numbers, is actually 17 milliseconds with the graphical network. So when we're using the graphical network to do global bundle adjustment, we're around 17 milliseconds compared to the control standard where we're using about almost 3,000 milliseconds. So we have an advantage in time. Accuracy is just the area. So to address accuracy, right? We talked about the global bundle adjustment, right? We try to do training data and we try and fix it to make it look better, right? But like, what I realized, I had to go back to the actual literature, and I'm actually training and fixing the global bundle adjustment where the actual inspiration came that I looked at it was actually training on and operating on a local bundle adjustment, which is actually here over during the local mapping phase, right? So it was a mistake on my part. But by looking at that, I said, wait, so what if I use some training data from the local bundle adjustment and see if we can get better results than what we see right here, right? Didn't quite get to the mapping, but I was able to get to at least look at the raw data of just the points, right? So let's just say I have 2 points. I have my predicted and I have what the actual ground truth is, right? If they are the same, they'll be right smack in the middle on that red line. And so we're trying to see if all these points can be on this red line. Now, all these points between my X and my Y is X, Y, and Z for 3 graphs. The X and the Y are kind of in the same spot, so it's a little biased, right? And it's just saying it's a little off right there. But we see some variation a little bit with the Z to where we say maybe we are seeing something here. Now I have to go back and do some data, and the extraction of the local bundle adjustment runs was very difficult, but I was able to get almost 1,000 different map points. So I was able to get a good sample size. Now I just have to make sure I just train them right and put it together. But like I said, data might be a little skewed, but it's promising. We have to get to that point. So the key takeaways, right? There were particular challenges with the graphical network and loop closing, right? But we were able to standardize the figure of merit, so like the map point errors, 3D reprojection, and then finding the full algorithm looking at the mean time. Then we were able to see a clear advantage in the graphical network over the traditional level required by just time. So now we have some new questions, right? What's the best neural network to even use with this, right? Now we are focused on graphical network, but is there a better one that can actually give us a better speed up or different results? Is there a data bias, right? This was just between one data set and then I did try to do another one with the teddy bear, right? But I still have other data to see if we have a data bias to see how it handles, right? Then how do you maximize the advantages a little bit harder way? Like we're doing this speed up not to just run this in the cloud, right? We want to put this on actual sensors, on an actual sensor. That sensor has to be very fitting, so it has to be very small. So we have to see how we can make this work on limited hardware. So that's what gets us in the future where it's actually why I even call it quantum corners, right? Once we start getting into understanding how we get to accuracy, now we can get specific to how we break things down and we're doing things like object detection, right? Just how we had before, I had this big old picture and I wanted to isolate the teddy bear. When we get into better, more understanding how we do accuracy, we can add more sensors to be able to get more accurate maps and more accurate images to be able to focus in on things. One of the papers that inspired me, I actually used quantum technology, quantum principles to be able to do superposition and entanglement between two lasers to create more of like a quantum lighter. With that quantum lighter, they're able to basically take an application to where they're able to change the image that you see when you use the quantum light. So what does that application look like, right? Right here, right? When the quantum light is on, you see the skater. When it's off, you see the car. Now imagine you're driving in your car, right? And you're able to see the whole view, right? But we're able to use actually that quantum light principle with the LiDAR to where now we can focus on certain objects. Hence, going back to our original, be able to focus on different fire trucks, emergency vehicles, so where we can now zoom in and get accurate information and focus in on them and get real time 3D graphs. Long way, right? But the whole thing was to build a foundation to see how we can realize and get there. I presented this before, so this is like, I post like my YouTube link to do see like you want to see like how far I've come. I need to start talking last year too. But I want to definitely give acknowledgments to definitely IBM Quantum Center who helped me with a lot of this research. Just putting me in this quantum realm. Intel for the NUC is actually running over there. If you want to see the algorithm, I have it like going over there. But they gave out the NUC to where I'm able to run it, and it's very small, so I was able to bring it over here. It's very high power computing. And Boeing, because they're very interested in this kind of signal technology and using like machine learning. So they helped me out a lot. And my professor, Dr. Sebron, and Dr. Amu, who also got me into STEM stuff. So, any questions?